Good afternoon, everyone. My name is Chi Huang, and currently I'm a graduate student at Cornell. Last year, I had a very interesting opportunity to work with Facebook on analysis of their entire photo serving stack, especially about their caching tiers. Today, I want to share with you what we have learned from this process. This is a joint effort of researchers from Cornell, Princeton, and Facebook. Facebook today stores over 250 billion photos, and the number is still increasing at a faster pace. If you take a look at a typical Facebook page, you cannot see photos everywhere. Profiles, newsfeed, or album that you share from friends. I saw a lot of white tiger photos yesterday from my friends' albums. So this is a very important application, and engineers have put a lot of effort to deliver good performance, including building an entire system stack. At the bottom, they have a customized storage backend called Haystack. Many of you already have heard about it. On top, there are multiple layers of cache between clients and storage. In our work, we'll look at every layer of the full stack. We want to understand how each layer performs, how we can improve it, and more importantly, what lessons we can gain for future system designers. To give you a preview of our results, regarding the current stack, we found all caches combining together have provided a significant traffic reduction for storage backend. And among them, browser cache is really important by absorbing over 65% of requests. Photo popularity distribution changes across different layers, and they impacted performance at every layer. For improvement, we promote a smarter algorithm called quadruply segmented RU, or S4RU for short, to improve the performance of current stack. And also point out that collaborative caching is actually worth trying direction in the future. Through the rest of the talk, I'm going to show you how we derive each lesson for you. But first, let's get a background knowledge. How the Facebook stack serves the photo request. Some of you might be checking Facebook right now. I wouldn't blame you. That's popular. The first thing showed up in your browser when you type facebook.com is the HTML file with photo URLs. You got to check the photo in the browser cache at first. The cache is usually small, and it's shared among multiple surfaces. But it is also insanely largely distributed. In our trace, we'll have seen over millions of them. If the photo is not found in the browser, then the browser needs to download the photo based on the URL from the Facebook stack, where I mentioned they have both storage and a cache servers. It's also known that Facebook uses CDN like Akamai to share the low-sum set of photos. But in our work, we only focus on the Facebook stack, where we have access to every layer. The first layer you're going to reach inside the Facebook stack is called Edge Cache. Currently, it's deploying at tens of locations called Internet Points of Presence, or POPs, across US. The purpose of this layer is to reduce cross-country traffic and also the data center bandwidth consumption, so you can save bandwidth for some interactive communications rather than static content. For this purpose, every edge cache works independently to cover clients from nearby region, and currently they run FIFO eviction algorithm. Let's suppose a browser sent a request, then Facebook DNS resolver is going to try to find the best edge location based on latency. In this case, let's assume the request from this location route to New York. If the photo is now found in the edge, then the request needs to travel further to Facebook data center, where they host additional layer of cache called origin. Origin cache are currently deployed at 4 data centers across the US, 2 on the East Coast and 2 on the West Coast. They have thousands of machines. They don't talk to each other, but you still should treat them as a single cache unit, because they route request from edge to origin by consistent hashing of the photo URLs. You might guess that a lot of cross-country traffic in that case. The reason is, compared to latency, the purpose for this layer is trying to protect the I/O bounded operation on the storage side. So they really want to maximize the hit ratio to combining all the cache space. Let's assume every data center owns a quarter of the consistent hashing space. And if you hash the photo URL, points to the data center hosted in Oregon. It's far away from New York. But in that case, the request needs to route to Oregon data center. If the photo is still not found in the origin cache, then you really need to reach the backend called Haystack. Haystack servers are co-located with origin servers in the same set of data centers. And the photos are replicated at different locations to provide both availability and reliability. Whenever a local replica is available, it's always favored by the origin cache for the sake of latency. But operating at this large scale, failures can happen. And the cross data center traffic needs to be generated to fetch a remote replica. So everyone is on the same page now. You know how the system stack works. And I showed you a bunch of lessons earlier. How can we extract the lessons from this stack? We decided to collect the trace in the production. The ideal scenario is that we can collect the trace at every component on this graph. You know, I'm a foreigner student. Touching human brain is a little bit sensitive. Instead, we access every layer that we have from browser to the backend, which means we drop the JavaScript running in every browser accessing Facebook. So thanks for help us collecting data when you use Facebook. We also modified the production code on Facebook servers across the layer so we can really watch the traffic flowing through the entire stack. There's a lot of traffic, so we have to do sampling. And the sampling method we pick is based on objects. What does it mean? In general, when you're trying to sample workload, you have two options. You can sample based on the number of requests you have seen, or you can sample based on the objects you're serving and collect the requests for those sampled objects. It turns out to be tricky picking one of them when you're dealing with a client-generated workload, because by conventional wisdom, that follows a power law distribution. Serving as an analogy, I'm just showing you a dummy workload following a power law distribution and plot it in the log-log scale. I promise you, I'm going to show you the real workload later. The x-axis is the rank of the object in terms of popularity. So left side is popular, right side is unpopular. The y-axis is the number of requests for different objects. So when you're sampling this kind of workload, doing request-based, you're very likely to miss unpopular objects because you just get access so few times. And statistically, you can miss them. In that case, you're going to generate workload with bias to popular content. And using that workload to evaluate the cache performance, you're going to inflate the cache hit ratio, which is not good. Another solution, which we think better, is based on the objects. No matter if it's popular or unpopular, you're sampling an object base. Then, by collecting all the requests for all the objects we sample, you can still get the same shape of the traffic. So we picked this option. And based on the hashing of a random generated photo IDs, we'll collect 1.4 million photos and look at the traffic accessing all those photos. But 1.4 million number is not the real number of objects we have seen in the cache. Why? Facebook also resizes photos for different application scenarios and also screen sizes. So they have an additional layer called resizer conducting this computation between origin cache and the backend. And after resizing, every photo variant is a distinct object stored in the cache. So what it means in the end, we collect the traffic for 2.6 million photo objects. And we conduct this instrumentation for a whole month, collect over 77.2 million requests generated from over 12 million browsers, and watch them travel through over 12,000 servers, including both cache and storage. This is a really rich set of trace from a deep and distributed stack. In our paper, we did a whole bunch of analysis. But in this talk, I'm going to only highlight on 3 of them that help us derive the lessons I showed you earlier. We take a look at how the traffic sheltering effects of the caches in terms of number of requests being absorbed by different layers. We look at the photo popularity distribution and how they impact the performance. We also use the production trace to evaluate our improvement ideas, like adding more space, training smarter algorithms, or using collaborative caching on the edge. Due to the time limitation, there are more interesting results I cannot cover, but I encourage you to talk to me after the presentation. First, let's derive how the traffic sheltering affects at every layer. Among the 77.2 million requests we have seen in the browser, over 65 of them are satisfied by browser hit. The hit ratio is significantly higher than the number we know from Chrome developers, which is about 40% for general content. What does it mean? It means the Facebook photo workload is very cacheable even for a single user. In an easy word, you just see the photos of friends over and over again. The miss in the browser generates about 26.6 million requests sent to the Facebook edge. And the hit ratio on the edge is about 58%. It is a still decent hit ratio. And you look at the photos they're covering, edge cache tends to be efficient on a different set of photos comparing to browser. And one interesting example we found is called viral photos. Imagine Justin Bieber or Lady Gaga uploaded photo. They're so popular to attract sort of millions of requests, but unlikely you're going to see many times over and over. For that kind of photo, browser cache is of very limited use, but the edge cache can be quite efficient. The miss in edge generates about 11.2 million requests sent to the Facebook data centers, and the hit ratio on the origin cache is about 31.8%. It is the lowest among all three layers of cache, which is not surprising, because when the workload reaches space data center, it just becomes less cacheable. In the end, storage absorbs about 7.6 million requests. When we translate this number into percent of requests served by different layers, now we derive the first lesson. All the caches combined together have sheltered over 90% of requests. Haystack Backend, in the end, only needs to serve a little bit less than 10%. Later, I'm going to show you we can even make it better. But let's switch gear to the second lesson, how the popularity of photos changes across different layers, and how they impact the cache performance. I promise I'm going to show you the real workload, and here it is. It is the workload we have seen on the browser, plot in log-log scale. Still, x-axis is the rank of objects in terms of popularity. Y-axis is a fraction of requests attributed for each object, comparing the entire traffic we have seen on the layer. That's a lot of information. Let me give you an example. For example, the most popular object we have seen in the browser trace accounts for about 2% of requests. And look at the shape. It does resemble a power law distribution, which agrees with conventional wisdom. But how about different layer? When you look at edge, well, after browser cache, the curve starts to tilt a little bit. It means the more popular the difference of popularity between popular and unpopular photos becomes less dramatic. But there is one exception. Let's take a hat. That one photo becomes even more popular than other photos after browser cache. When we look at a trace, that is the viral photo we have talked about. They have millions of requests, but all from different clients. When we look at origin, the shape changes a lot. The skewness is reduced after both browser and edge cache, and the shape even starts to deviate from a power law distribution. More interesting, when we look at the backend, you see it even starts to resemble a different distribution we call stretched exponential. In easier word, it has a very fat head and a thin tail. When you're designing a storage system for this kind of workload, you should focus less on caching as much as caching tiers. We also replot the curve by replacing y-axis with the absolute traffic amount. And here are how the curves look like. We believe those curves are important to share with system designers. If you're designing with a storage or cache, you really need to think which layer your system is going to be deployed and which workload you should perceive. That can impact your system performance. As an example, I'm going to show you how it impacts our cache performance. Based on the workload we have seen in the browser, we bin the photos in 4 categories based on the popularity: high, medium, low, and lowest. And all of them accounts for equally 25% of requests. Then we plot how much percent of requests from different categories have been served by different layers. First is browser. We can see the percent shared by browser decreases gradually when the photo gets less and less popular. But when we look at edge, it's very interesting. It holds a consistent share of traffic, about 22 to 23% for all top 3 categories. The only exception is when the photo gets less popular than 1 million others. And for instance, the lowest group, the edge cache traffic share drops to about 7.8%. How about origin cache? It contributes most in the low group. Photos in that group just not that popular enough to be residing in browser or edge cache, but still more cacheable compared to the lowest group. Haystack Backend really serves the tail. When you look at the traffic generated in the lowest group, it accounts for about 70% of the entire Haystack workload. So now we have derived the second lesson, how the popularity changes at different layers, and how they shape the system performance. The next question we ask is, how can we make it better? We try a different method by running simulation without collecting trace. We replay the trace by using 25% of them to warm up the cache. 25% of trace in a month counts about a week. The current life cycle of a photo object in Facebook stack is less than a week. So we believe after warming up the cache, it is really warmed up. And using the next 75% to justify the hit ratio is not by us. It turns out to be tricky to estimate the current deployment size in our simulator because we're working on a limited set of photos. I'm going to show you how we overcome that problem. We evaluate hit ratio both on the object-wise and byte-wise. But in this talk, I only focus on the object-wise. First, we did a simulation on the edge trace where we collected in San Jose. It is a high traffic edge we have seen in the trace, and also has a median hit ratio among all the edge caches. Then we replay trace by knowing its current FIFO algorithm with different cache size. Through the observation, we know the current hit ratio is 59%. So we can estimate the current deployment size by finding the hit ratio. Using the same curve that we can see, if we want to double in the cache capacity, we can increase the hit ratio to 65%. Tripleizing gives a little further improvement to 68%. Out of curiosity, we want to see what's the upper bound. So we'll run the simulator with infinite cache capacity that we can hold the entire working set. Then the hit ratio is a little less than 85%. So if we want to reach that line just by dumping more hardware, how much will we need? It's about 45 times of the current cache capacity. That is insane, a lot of money. You don't want to burn that. But fortunately, we can try better algorithms. We first try LRU and IRFU. Both are widely known and easy to implement. They work slightly better than FIFO, but not that exciting. We will also try a whole bunch of other algorithms through literature. The final winner is S4LRU. What does it mean? What is S4LRU? Well, in general, what is a segmented LRU? It is an algorithm that separates the entire cache space into 4 segments with different levels. Then you run LRU on each level. When you have a miss object, just put it into the lowest level segment. When you have a hit, you promote it into a higher level segment. When you need to evict the object, just depromote it into a lower segment. So in another sense, it's a combination of LRU and LFU. And the parameter 4 is actually counts the way in between recency and frequency to decide which object you should cache. We tried a bunch of parameters. 4 is the sweet spot, works the best in our workload. Let's take a look how S4LRU works. By keeping the cache capacity, same cache capacity, you can get the same hit ratio improvement as you're tripleizing the cache capacity using FIFO. If you're satisfied with the current 59 hit ratio, okay, S4LRU can save you about 2/3 of the hardware cost. Is there any upper bound for algorithm? We also try simulating the Belletti algorithm, which just knows the future and kind of like serves as optimal for algorithm improvement. It shows there's still a lot of space between the optimal and S4LRU. We also did the same simulation on origin cache, and the results agrees what we found for the edge. And more importantly, S4LRU gives us more improvement compared to edge. So currently, Facebook is investigating implementing S4LRU in the hardware on origin. If it works, then push to the edge. As academics, we also want to ask a question. Can we get closer to the optimal algorithm by now knowing the future? The more fundamental question is, which photo, when we see in a workload, should we cache? We propose S4RU because it understands two signals, recency and frequency. Are there any more signals? We also look into the metadata of the photo. Look at like the age of the photo and the social connectivity of the photo. We found very interesting results. But meanwhile, to derive more questions, the answer in this, the first question we want to ask. So I'm going to leave those results out of the main talk. I encourage you to talk to me after the presentation. And you use the last time to derive the last lesson about collaborative caching. Earlier, I mentioned intuitively, every edge cache only needs to cover local region clients. Two benefits. One is the latency. The second is a limited working set that you can help with the cache performance. But Facebook also routes requested different edge caches for a bunch of operational reasons, like narrow capacity of different edge, peering cost in terms of money. So how does that impact cache performance? We took the trace from the 9 high traffic volume edges and look at the client requests sent from the local regions and see how much of them stay. When we look at Atlanta, even though they have edge cache in the city, only 20% of them stays local. The rest 80% goes everywhere. Is Atlanta the only case? We also look at other cities. It turns out the remote traffic is a normal case. From the perspective of edge, it's actually serving an amplified working set by covering more regions. That can hurt the hit ratio. Can we make it better? Well, you already route requests everywhere. So let's throw some crazy idea. Just routing requests from clients to edge by using consistent hashing, like we did for origin. Here I'm showing you the current hit ratio, about 59% when they're working independently. When we collaborate them, we can get over 18% improvement. So that gives us a very interesting direction you can further looking into. Clearly, there's a long line of previous work in our area, and all of them deeply inspired us. But to conclude, I want to mention a list of unique contributions we have bring here. By analyzing a very unique data set from a deep and distributed production system, we have quantified the performance at every layer and how they correlate with popular distribution changes. By recognizing both recency and frequency, we propose S4RU as an improvement for the current stack. There are more metadata also worth further looking into, whether we can counter more factors to get better algorithms. We also want to outline the potential improvement by using collaborative caching. That's the end of my talk. Thanks for your patience, and now I would like to take questions.
So first up, we'll take a question from the internet. So one very popular question was, why is the hit rate on the browser cache so high? So is it really just that users have 5 photos they just look at repeatedly, like Gollum looking at the precious, or is there some deeper explanation for what's going on there?
So one typical example that has this trend is the profile photos. For example, like I haven't upgraded my profile photo for probably a year. So all my friends for the past year just see my same profiles over and over again. That kind of photos can inflate the cache performance in browser, definitely. But for other photos, we haven't looked into like how much they contribute and how much repeated requests they've seen. That's kind of interesting. We're going to look into it next.
Parijat Aditya from MPISWS. You mentioned Facebook uses a commercial CDN such as Akamai. So what point on this stack does the CDN come in, and on what heuristics do you decide when to fall back on that CDN?
Sure. So, I mean, the Facebook controls how much traffic should route it to Facebook Stack and Akamai, and they do that by generating different URLs. So right from browsers, they diverge. But the Akamai still needs to go back to the Facebook's backend, and they actually need to go through the resizer. So that's where they merge back. I mean, Akamai, we don't have access to Akamai, so it's kind of like a black box for us, so we didn't collect trace for them. And our focus is carrying the Facebook stack. That's how we separate the trace.
So it branches from the browser itself?
Yes.
Okay.
And we also look into the backend, because, I mean, we don't want like the trace from Akamai to backend.
Right, thanks.
Hi, Imer Vikmason, Reykjavik University. nice talk. Illuminating to see how things work at scale like that. I'm a little bit curious about your cache replacement algorithm. So you're talking about recency and frequency, and this is a discussion that's been going on for over a decade in the cache literature. So I wanted to ask you if you looked into things like ARC and CAR and LIRS and ClockPro and all these things that explicitly make the trade-off between recency and frequency.
So, I mean, unfortunately, there's really no canonical list of all the algorithms people have provided. So when we do the simulation, we kind of like look into the literature we can find, and also the algorithms are easy to implement. We look at it from this different perspective, like a lot of variants of LRU, a lot of variants of LFU. All of them are kind of looking into trading between recency and frequency. And among them, S4RU is works the best, easy to implement. We haven't tried other algorithms, but I would like to try. If you can point me to more algorithms.
Mm-hmm. Thank you.
So another question from the internet is, will these traces be made available to other researchers? I don't know if you can answer that.
Well, send your students to Facebook doing internship, or your professor spend a sabbatical there.
Okay, so I guess the answer is maybe.
So I think another important perspective is prefetching. I'm not sure if you have investigated the effect of prefetching. Maybe that contributes to the high hit ratio on the browser cache.
So you're talking about prefetching is on the
Right.
browser or general caching tiers?
In general, but most specifically in browser. For example, I viewed the first photo in an album. Maybe you want to prefetch the other photos.
So a lot of them have to be made a decision by application in your scenario. But in our case, when we look at the caching algorithm in general, we're looking like what signals can show the photo should be cached for all applications. So that's why we take a look at the age, the photo of the age of the photo, sorry, and also like how popular the owner is. We found very interesting results, like when the photo is young, it attracts a lot of traffic comparing when the photo gets old, which is reasonable. And if your owner is like a super popular, like have millions of fans, you also tend to be, attract more traffic. So those are two interesting directions we think about going to, but we haven't verified whether they're going to really improve the cache performance, like how much they can differentiate from the already we found the signal, like a recency and frequency. So that's like a future direction we want to look into, but now I don't have the results yet.
All right, thank you.
All right, we'll take one final question from the internet, which is, do you have any idea how much extra bandwidth would be consumed if you move the resizing operation closer to the clients?
Very good question. Because of deadline, we couldn't finish that simulation. But we're looking into it. Hopefully we can have a result soon. That's definitely something we want to look at.
Great, let's thank the speaker.